Hello, this is Dr. Nak, and we're going to go over section 10.4, polar coordinates and polar graphs. So instead of representing a point in the rectangular coordinate system, like x, y, we're going to represent the point in the polar coordinate system as follows. To form the polar coordinate system in the plane, we must fix a point O called a pole. So let me just fix a point, and then I'm going to call it O. This is called a pole, or the origin, so I'm just going to write it as origin. Alright, now from here, we're going to construct from O an initial ray called the polar axis. So this line right here is called the polar axis. Then each point in the plane can be assigned polar coordinates as follows. So let me just pick a point in the plane. So let me just go, suppose this is our point. Alright, so I'm going to call that point P, but instead of calling that point as x, y, in polar coordinate system, we call this r, theta. R is a radius and theta is an angle. So let me just draw the straight line. And this becomes our r, and then of course this angle here becomes the theta. Now r is called the directed distance from O to P, and theta is the directed angle counterclockwise from the polar axis to the line segment OP. So what the heck is the directed distance, right? Well, distance usually is positive, but directed distance, your distance can be negative. And same thing as our angle theta. Our angle theta can be positive or negative, just like what we learned in trigonometry class. And the system is said to be in standard form when the pole is at the 0, 0, which is at the origin, and the polar axis is the positive x-axis. So going back to this picture, let me see. Let's call our pole to be 0, 0, and then let's make our polar axis to be the x-axis. Now we say that the system is in standard form. Now let's go over some of the big differences between the rectangular coordinate system and the polar coordinate system. So our good old rectangular system, our graphing paper kind of looks like this. Alright, and we can just have plot one point. Let's just say maybe we can plot right here. So what is that? That's 1, 2, let's just say 1, 2, 3, and 1, 2, 3, 4, 5. So this point right here is represented by x equals to 3 and y equals to 5. Now notice that there is no other way that we can express this point. This point, no matter what, is only 3, 5. Now let's look at the polar system. So polar graph is going to look something like this. So each circle is called the radial lines. So this circle here, we could call this, it has a radius of 1, and this is another radial line of radius of 2. You get the idea. So if I get this radial line, this will be the radius of 3. Now let me pick a point. So maybe I'm going to pick this point, and I'm going to call this point P. Now again, in a polar system, a point can be represented by r, theta. So let me just write it on this side, r, theta. Whereas on the rectangular system, this is x, y. So let me just write it down below. Polar system is represented by r, theta. Now let me draw a circle here where the point is. Oh my gosh. All right. Anyways, okay, so here's another radial line of radius of, what is that? 1, 2, 3, 4, 5, 6. So here our r is 6. Let me just write that out in a different color maybe. So here it is. Now let's talk about this point. Do you see that just like when we learned in trigonometry class, we can represent that point in infinitely many ways. So right now, let me just call this point P. I'm going to bring it up here. So our P is represented by r, theta. So right now we have r is 6, and then theta is going to be pi over 3. Now if I move counterclockwise from our p, and then we revolve one revolution, which will be 2 pi, do you see that we're going to get to the same point again? So in this case, this point can be represented as r is 6, and then pi over 3 plus 2 pi is 7 pi over 3. So 6 comma pi over 3 and 6 comma 7 pi over 3 represent the same exact point. So again, in polar coordinate system, we can represent a point in infinitely many ways, whereas rectangular system, there is one and only one representation for point P. Now let's analyze this a little bit more. So what I did here was I plotted the same point P, which was 6 comma pi over 3. So here our r is in fact positive 6. And then pi over 3 was found by starting from the positive x-axis, revolving towards our point P. So let me just first jot down where the positive 6 would be. So it's 1, 2, 3, 4, 5, 6. So this point should be positive 6, then the other way should be negative 6, isn't it? So I'm going to jot this down as negative 6. Now, starting from when r equals the positive 6, if I revolve counterclockwise to pi over 3 radians, then we're going to get to that point, which is represented by 6 comma pi over 3. Now, we can also start from r equals to negative 6. So if I start from r equals to negative 6, and if I go counterclockwise towards the same exact point P, let me just get there. All right, so this here can be represented by r equals to negative 6, and then our angle theta is pi, which is 180 degrees plus the 60 degrees. So let me just do the calculation on the side. So 180 is pi, and 60 degrees is pi over 3. So what the heck is that, 4 pi over 3? So this point P also can be represented by starting from negative 6, r equals to negative 6, and you're going to revolve positive 4 pi over 3 to get to that point. Alrighty, I think we're ready to do some examples, so let's take a look. Example 1, plot the point in the polar coordinate system and give two other points that represents the same point. So let's do a couple of them. So part A, our point P is 3 comma pi over 6. So let me first jot down where the 3 is. So 1, 2, wait, hold on. 1, 2, my eyes. Wait, 1, 2, 3. I think this is 3. And then, what the heck? Let me just jot down negative 3. 1, 2, and a 3. So is this negative 3? All right, so let's first plot our point P, which is 3 comma pi over 6. So that will be starting from positive 3. You're going to revolve pi over 6 units. So here, let me see, changing the color. I'm going to go, is this pi over 6? Yeah. All right, so let me make a dot. So that will be this point right here is what we're talking about. So let me label this point as 3 comma pi over 6. All right, now let's try to come up with two other points that's going to represent the same exact point. So how about, let's start from negative 3, shall we? All right, so if I'm going to start from negative 3, let's move counterclockwise, so that means that our angle is going to be positive. So let's start from negative 3, and I'm going to revolve towards that point, and then here we are. So another representation would be starting from negative 3. How much do we revolve? So we got pi plus, what is that, pi over 6? So let me just work it on the side. Pi plus pi over 6, so that will be 7 pi over 6. So that's another representation. So we got negative 3 comma 7 pi over 6. All right, so let's try to come up with another one. I don't know where you want to start. So you want to start from positive 3 or negative 3? Let's go with negative 3. All right, so I'm going to start from negative 3. And let's go clockwise towards the point P. So meaning starting from negative 3, I'm going to revolve to here. Okay, so in that case, our point P, starting point is negative 3. And how much do we revolve? 90 plus 60. So this is same thing as 90 is pi over 2. Plus 60 degrees is pi over 3, which is 5 pi over 6. Alright, so another representation will be negative 3 comma 5 pi over 6. Okay, part B. You try this one. So please plot where 2 comma negative pi over 3 is going to be. Then try to come up with 2 points that's going to represent the same point. Just so that we can see the radial lines better, so I'm going to make this grid as, so here is our radial line of 1, radius of 1, and I'm going to make that radius of 2, radius of 3, and so forth. So this means that this is going to be negative 1, so this will be negative 2. All right, get to work. All right, so I'm going to plot 2 comma negative pi over 3. So starting from positive 2, I'm going to revolve negative pi over 3, which is negative 60 degrees. So let me see. Starting from 3, no, just kidding. Starting from 2, we're going to go negative 60 degrees. Does that look right? I think that's right. But so here is the point P, which is 2 comma negative pi over 3. So negative pi over 3, I went, starting from 2, I went downward pi over 3 units. Okay, now let's go with another point. So how about we start from negative 2? Alright, now starting from negative 2, should we go towards positive side of the angle? Negative. Let's do positive side first. Alright, so starting from negative 2, I'm going to revolve counterclockwise to get to that point P. So in this case, starting from negative 2, we went 90 degrees, which is pi over 2. And then you're going to have to add on 30 degrees, which is pi over 6. So here we got pi over 2 plus the pi over 6, which is 4 pi over 6, and which is same thing as 2 pi over 3. Alright, so another representation is negative 2 comma 2 pi over 3. Alright, so let's just do another one. What did you guys come up with? So let me start from P equals to, not P, sorry, R equals to 2, positive 2. And let's revolve towards the positive side maybe. So starting from positive 2, I'm going to revolve counterclockwise to get to that point. Alright, so how much do we revolve? Well, we got 270 degrees, which is 3 pi over 2. And then we went 30 degrees more, so which will be pi over 6. So that's 10 pi over 6. And that's what, 5 pi over 3. Okay, so another point representation will be 2 comma 5 pi over 3. I think this is good enough. I'm hoping that you're understanding this, but of course, if you have any questions, please ask. Okay, our next very, very important topic is coordinate conversion. So suppose we're given a point on the rectangular coordinate system, which will be x comma y. Now, what we want to do is we want to represent that same exact point in a polar coordinate system. So suppose this is our rectangular coordinate system, and I'm just going to choose a point P. So our point P right now is in terms of x comma y. Now, our job is this. How can I represent the same point in polar coordinate system? Meaning, how can I go from xy to r comma theta? And vice versa. Suppose you were given a point in terms of r comma theta, how do I convert that back into a rectangular point, which is x comma y? Now, instead of just writing down all the conversion formulas, let's try to understand why that's true. Alright, so right now let's suppose that this is our x-axis and this is our y-axis, and then our point P is, boom, right there. So let me just draw a line from the origin to point P. And from there, from point P, I'm going to draw a perpendicular line towards the x-axis. So if I did that, distance from here to here, let's just call this guy x. And then distance from here to here, that will be y. And let's call from here to here is our angle theta. Alright, now let's look at that right triangle and let's compute the tangent of theta. So let me just write it as tangent of theta. Alright, so those of you who do the adjacent over hypotenuse and yada yada yada, a lot of students memorize this as SOHCAHTOA or something like that, right? But only bad thing about SOHCAHTOA is if you misspell it, then you're screwed. But anyways, so tangent is opposite over the adjacent, so the opposite side of angle theta, we got y, and then adjacent side will be x. Now let's compute sine of theta. Alright, so sine of theta is opposite over the hypotenuse, but hypotenuse is our r. Oops, did I erase the r or did I forget to write that r? But anyways, from here to here is r. Alright, so now let's go with the cosine. Cosine of theta is adjacent over the hypotenuse, right? So it's going to be x over r. Alright, and then we know that Pythagorean theorem, which is x squared plus y squared equals to r squared. Alright, now let's look at sine of theta being y over r. So can we solve for y from there? Yes, so this implies that what do we got? Y equals r sine of theta. Alright, now let's look at the cosine. Can we solve for x? Yes, we got x equals r cosine of theta. And guess what? That is our conversion formula. So here's our theorem, coordinate conversion. So we're gonna have to memorize all of this, so please memorize that. X equals r cosine of theta, and then y is r sine of theta. And also we're given that tan of theta is y over x, and x squared plus the y squared equals to r squared. Please memorize this, and then if you forget, I'm hoping that you know how to derive it. But anyways, here it is. So these will convert from rectangular to polar and polar to rectangular. Let's do some examples. Example 2, convert the polar coordinate to rectangular coordinate. So what we're given here is r is -2 and our theta is 11 pi over 6. So what we want to do is we want to represent the same exact point in terms of x comma y. Let's first plot where that point is going to be on the polar coordinate system. Okay, so we're going to start from r equals to -2, so we're going to start from here. And we're going to revolve positive 11 pi over 6 from there, which means that we're going to have to move counterclockwise 11 pi over 6 units. Now, since pi over 6 is 30 degrees, so if you're still like meh on the radian measure, you can always convert that in terms of a degree. So we got 30 times 11, which will be 330. So we're going to have to revolve 330 degrees counterclockwise. So let me just do that. So let me just go around this radial line, and I'm going to plot this point right here. So this point right here is our -2, 11 pi over 6. Now what we want to do is we want to convert that in terms of a rectangular coordinate system, which is x comma y. So what do? We're going to have to use that conversion formula, so let's do it. So our x is our cosine of theta, and then y is our sine of theta. Okay, so let's work with the x first. So we're going to have r equals negative 2 cosine of 11 pi over 6, which is same thing as negative 2 times, what is that, cosine of 11 pi over 6? 11 pi over 6 is 330. That lies in quadrant 4. So that means that cosine is positive there. So here what we're going to get is square root of 3 over 2, which will give us negative square root of 3. All right, now let's go with the y. So y is r sine of theta. So this is negative 2. And then sine of 11 pi over 6. Now again, 11 pi over 6 lies in quadrant 4, so sine is negative there. So this is same thing as negative sine of pi over 6 if you like to use the reference angle theorem. But in any case, this is going to be negative 2 times, what is that, negative 1/2? So which is going to give us just positive 1. So therefore, our rectangular coordinate is going to be negative square root of 3, comma 1. So this is what the question's asking you to find. Now let's double check to make sure that this makes sense. If you look at the picture above, the point that we plotted, let me just circle it in different color here. This point right here, let's see, our x value better be negative, and then our y value is positive. So does it make sense? Is our x value negative? Yes. Is our y value positive? Yes. So what we just discovered is this point right here, if you have to express in terms of a rectangular coordinate, this exactly the same point is negative square root of 3, comma 1. Now let's take a look at another example. So let's work backwards. So we just went polar to rectangular. So let's practice how to go from rectangular to polar. So here's our example 3. Given the rectangular coordinate 3 comma negative square root of 3, find two sets of polar coordinates for the point 4 theta between 0 and 2 pi. So before we do anything, let's just plot our point, which is represented by 3 comma negative square root of 3. So we got x equals to 3 and y is negative square root of 3, so that's approximately negative 1.7-ish, I think. So I think it will be around here. All right, so I'm going to plot this point as 3 comma negative square root of 3. So let me just go like this. All right, so now what we want to do is this. So right now what we're given is x comma y. So now what we want is we want to represent the same exact point in terms of the polar coordinate system now. So what can I do? How can I express this point in terms of r comma theta? So that's what the question's asking you to do. So let's first try to find our r. So let me just write every step out. So to find r, what we need to use is our Pythagorean theorem, which is x squared plus y squared equals to r squared. All right, so now I'm going to plug it in. Our x value is 3, so we got 3 squared plus our y is negative square root of 3 squared equals to r squared. All right, so we get 9 plus, what is that, 3 equals to r squared. So we get 12 equals r squared, so that implies that our r is going to be plus or minus square root of 12, so which is same thing as plus or minus 2 square root of 3. So let me just box that. Remember, r can be negative in a polar coordinate system. Now next step, let's try to find our angle theta. So let me just write to find theta. All right, which conversion formula have we not touched yet? Well, we have not touched tangent of theta equals y over x. So that's exactly what we need to use to find the angle theta. So we get tan of theta equals y over x. So that implies that we're going to have tangent of theta equals y is negative square root of 3, and then x is 3. So now we need to take the arctangent on both sides to get theta equals to arctan of negative square root of 3 over 3, which implies that, what is that? Our theta value is going to be, one of them should be 5 pi over 6, and then 11 pi over 6. So let me just box this. Now we need to analyze a little bit. I have a feeling I'm going to run out of room on this page, so I'm going to go to the next page. Okay, so here what I did was I just plotted our point 3 comma negative square root of 3 on the polar graphing paper. Now remember that our r was plus or minus 2 square root of 3, and theta was 5 pi over 6, and then 11 pi over 6. Alright, so let me just box that because we need this information here. Alright, now 2 times the square root of 3 is approximately, I think approximately around 3.5-ish, I think. So this is around, I'm just going to say this is approximately 3.5. Alright, so notice that our point lies on the radial line approximately at 3.5, because look, so I would say this is approximately 3.5, and this is the approximate value for 2 square root of 3. And if I draw the radial line, then notice that our point does lie on that line. So now what we need to do is this. Since our r is positive and negative 2 square root of 3, we need to determine, if I start from positive 2 square root of 3, how can I revolve around that radial line to get to our point? Now, since they are both positive angles, we're going to have to move counterclockwise. So keep that in mind. Now, if I start from positive 3.5, or I should say 2 square root of 3, I need to revolve counterclockwise this way to get to that dot. So in this case, if I start from the positive of the radius, then I need to revolve 11 pi over 6, which is not approximately, it's exactly 330 degrees. So I'm just going to make a combination as r comma theta, starting from 2 root 3. Moving counterclockwise, I need to revolve 11 pi over 6 to get to our point. Now, when I start from negative 2 square root of 3, which will be this right here. I don't know if you can see that. All right, now, again, we're going to have to move counterclockwise because we're given the positive angle. So if I revolve from here, oh my gosh, all the way down to our point, we need to revolve 5 pi over 6, which is 150 degrees. So our combination is going to be negative 2 root 3 and 5 pi over 6. So this is going to be our final answer, which means that this point right here is exactly the same thing as 2 square root of 3 comma 11 pi over 6, and then negative 2 square root of 3 comma 5 pi over 6, and they're all equivalent. Equivalent meaning they all represent the same point. I hope you're getting a little bit comfortable with converting a point from polar to rectangular and rectangular to polar. So now what we're going to do is we're going to convert the rectangular equation to polar form and vice versa. So let's take a look at example 3. The question says, convert the rectangular equation to polar form and sketch its graph. The equation is given by 3x minus y plus 2 equals to 0. Since we're going to have to graph this, if I were you, I will just look at the rectangular equation to see what kind of figure that we're going to get. So right now we're given the rectangular formula, but notice that if I solve for y, let me just bring it over here. So y is just going to be, what is that? 3x minus 2. So this is nothing but an equation of a line with the slope 3 and y-intercept at negative 2. So even if we convert this into a polar form, that polar graph should be a straight line. So keep that in mind and let's get started on this one. So what we want is we don't want to see x and a y flying around anymore. Instead, I need to see something of the form r and then cosine and sine. All right, so what we want right now is if I can solve for r of theta explicitly, that will be awesome, but it could be implicit. But anyways, what we want is r of theta. Okay, so what do? Well, we already know that our x is our cosine of theta, and then our y is our sine of theta. So we're gonna use these two conversion formula to replace our x and a y. So then what we're gonna get is 3 times r cosine of theta minus y, which is r sine of theta, and then plus 2 equals to 0. Now, if you want to make this into a function r of theta, I think we can do it in this case because we can easily solve for r in terms of theta. So let me first factor the r out. So if I do that, we're going to have r times 3 cosine of theta, and then minus sine of theta. And then let me just bring that 2 on the other side, so which is equals to negative 2. And since I know for sure that cosine of theta minus sine of theta could never ever be 0, so I can divide it by that whole quantity. So what I'm going to do is I'm going to divide both sides by 3 cosine theta minus sine of theta to solve for r. So here what we're going to get is r equals negative 2 over 3 cosine, and then minus the sine. Now I think this is in terms of r of theta because we're able to solve for r, and then on the right hand side there is no more r. Everything is in terms of theta, so we can call this guy r of theta. It's a function of theta now. So this equation is in polar form. Now to sketch this, do you see that it's a lot easier for us to look at the rectangular equation, which is y equals 3x minus 2, instead of r equals negative 2 over 3 cosine theta minus sine of theta. So this is why I'm saying that if you have to sketch a graph, convert it into a rectangular form so you know what the graph's going to look like. So if I graph this out by looking at y equals 3x minus 2, I know for sure that our y-intercept is going to be at negative 2, and slope is 3. So you're going to go up 3, 1, 2, 3, and then over 1. And if I connect those dots, then that will be our equation, graph of the equation y equals 3x minus 2. All right, so suppose we didn't see that. Let's just say that, all right, I'm just going to graph the polar form because I did not realize that the rectangular form is going to be a straight line. You'll see how painful this is going to be. So let's suffer together for now. So let's pretend this is our x-axis and this is going to be our y-axis. And next, what I'm going to do is I'm going to make the chart in terms of r and theta. And I'm going to pick some random value for theta so that, I can compute the corresponding value of r. So let's pick some nice angles. So let's maybe go with 0, 30 degrees is what, pi over 6. And then 45, pi over 4. 60, pi over 3. Next one, let me just skip 2. I'll just go pi over 2. And I'm just going to skip the pi. And then 3 pi over 2. And then let's just go with 2 pi. Next, what we're going to do is we're going to find the corresponding value of r when theta is 0, pi over 6, and so forth. All right, so let's start out from 0. So when theta is 0, we're going to have negative 2 over 3 cosine of 0, and then minus the sine of 0, which is negative 2/3. And this is approximately negative 0.7-ish. I am converting into a decimal form because I need to plot each point along the radial line. And next, when theta equals to pi over 6, we're going to get negative 2 over 3 cosine of pi over 6 minus the sine of pi over 6. You see that this is really going to be complicated already to start out with. Since I would like a decimal form, I'm going to use my calculator. So I think this is approximately equaling to negative 0.95. Please tell me if I'm doing this wrong, if my trusty calculator is failing me here. All right, now let's go with when theta is pi over 4. Then what I got is a negative 1.41. And when it's pi over 3, I got corresponding r value to be negative 3.15. And when theta is pi over 2, I got 2. That's a nice number for once. All right, and when theta is pi, I get positive 2/3, which is approximately 0.7. And 3 pi over 2, I get negative 2. And then at 2 pi, I'm back at negative 2/3, which is negative 0.7. All right, so let me just make an ordered pair here. So we get when, what is that? R equals to approximately 0.7, our theta is 0. So this is of the form r comma theta now. All right, and then here we're going to get negative 0.95 comma pi over 6. Next one is negative 1.14 comma pi over 4. And negative 3.15 comma pi over 3. Yikes. And 2 comma pi over 2. And 0.7 comma pi, negative 2 comma 3 pi over 2. And negative 0.7 comma 2 pi. Alright, so let's just try to plot these points along the radial line. And you know what? Since we're dealing with the polar form, I'm going to erase this x and a y, because we're going to be graphing in polar form. Alright, so now let's get started on this one. Let me first make the radial line. Alright, I think we're good to go. So let's first plot r is negative 0.7 and theta is 0. So that will be maybe right here. And then the next one is negative 0.95 comma pi over 6. So I'm just going to plot there. And the next one, when theta is pi over 4, wait a minute. When theta is pi over 4, I don't think it's negative 1.14. I think it's negative 1.41. Oh my goodness. Sorry about that. So let me just change this. Negative 1.41 comma pi over 4. All right, so where in the heck is that? Maybe it's around, okay, maybe here. Is this pi over 4? Yep. All right, now the next one, what a pain in the butt, right? Next one is negative 3.15 comma pi over 3. So pi over 3, and then negative 3.1. So like maybe here. All right, next one, 2 comma pi over 2. I got that one. So positive 2 and pi over 2. I'm going to have to go this way. So there you go. Next one is 0.7 comma pi. So I'm going to start from positive 0.7. And, oh no, I'm just going to go this way. This way meaning counterclockwise. And guess what? I'm going to land in the same spot as negative 0.7 comma 0. And the next one, negative 2 comma 3 pi over 2, we're going to land in the same spot as 2 comma pi over 2. So it's already plotted there. And the last one, when theta is 2 pi, we're going to have negative 0.7 comma 2 pi. So again, we're back at when theta equals to 0, and we already plotted negative 0.7 comma 0 there. And now plug it in all 8 different values of theta, we could only get 1, 2, 3, 4 points plotted along the radial line. Wait a minute, I don't know how to count. 5 points along the radial line. So do you see that if I need to plot more points, especially in this case, I guess we could call this in quadrant 2, which will be in this in this region right here. Do you see that we're gonna have to plug in more different values of theta just so that we can plot more points along the radial lines. But since we're smart enough to figure it out that from the very beginning, this is going to be a straight line, how do we determine that is by looking at our rectangular equation. So we don't need to plot any more points because we already know that this is going to be a straight line. So all you have to do is connect those dots, and that is going to be our graph of r equals -2/3 cosine of theta minus sine of theta. All right, our next example is converting the polar equation to rectangular form. In example 3, we did it the other way around. Given rectangular, we converted that into a polar form. All right, but anyways, let's take a look. Convert the polar equation to rectangular form and sketch its graph. So we are given r equals 5 cosine of theta. And since we need to sketch this graph, what we learned from example 3 is do not try to sketch a polar form unless you already know what the figure is going to look like. So to sketch this graph, well, we need to convert this into a rectangular form anyway. So let's get started on this. All right, so by the way, this is a common final exam question for second semester calculus. So put a star next to it. You know what? I'm going to put a star next to it for you. Know this. All right. Okay, so let's see, what can we do here? So basically what we want to do is we don't want to see r and theta flying around anymore. I need to get rid of those, and in terms of r and theta, we need to replace that in terms of just using x and a y. So what to do? Well, let's note that we have x equals r cosine of theta. But right now, we're only given cosine of theta. But if I have a r in the front of it, or it doesn't matter, behind of cosine, do you see that I can convert that into x? And also, on the left-hand side, if I have r squared, then we can replace that with x squared plus the y squared. So regardless, on the left-hand side and the right-hand side, we need that extra r. And that is the trick. We need to multiply both sides of the equation by r. So I'm going to write that out. So the trick is to multiply both sides by r. All right, so now let's take a look. So I'm going to copy and paste the equation that we're given, 5 cosine of theta. All right, now we're going to multiply by r. So I'm going to put r here, and then maybe I could squeeze in r there. All right, so what do we get? So this implies that we're going to have r squared equals 5r cosine of theta. So far, so good? All right, but the thing is, r squared is, again, x squared plus the y squared. And so this is going to equal to 5, and then remember, r cosine of theta, this is nothing but x. So I'm going to replace that with x. So far we have x squared plus y squared equals to 5x. All right, now let's determine what kind of figure this is going to be. So let me just bring the 5x on the left-hand side. You get x squared minus 5x plus the y squared equals to 0. What do you think? I think this is going to be either an ellipse or the circle. But regardless, do you see that we're going to have to complete the square on the x? So let's do it. So here I'm going to write it as x squared minus 5x. And now I'm going to leave a little room, and then plus y squared equals to 0. All right, completing the square. So first I'm going to divide the middle number by 2. Then here I'm going to get -5/2. And what goes in here is -5/2 squared. That's the quantity that you need to add in. So here I need to add in plus 25/4. And that means that I'm going to add 25/4 on the right-hand side of the equation as well. Now the first 3 terms are going to become the perfect squared. So here what we're going to get is x minus 5/2 squared plus the y squared equals 25/4. So what kind of figure is this? this is nothing but an equation of the circle centered at 5/2, 0. But let me first box this rectangular equation because this is the first part of the question. So let me just write this as rectangular equation. All right, now we notice that this is going to be a circle centered at 5/2, 0, and the radius of 5/2. Be careful there. The right hand side is r squared equals to 25/4, so our r is 5/2. So let me box that because we need to sketch this. Alright, so this is centered at 5/2, which is 2.5, 0, so that will be here. So I'm just going to write this as 5/2, 0. Let me change the color. Alright, and the radius of 5/2. So radius of 5/2, oh, that's perfect. It's going to touch here at the origin, and then this point right here will be, what is that? 1, 2, 3, 4, 5. Alright, so then, oh my gosh, I have to graph this out. You know what, before I do that, let me go upward 2.5 units because that's the radius. Completely drawn off the scale. And for the bottom from the center, 2.5. Oh my gosh, this is going to be one ugly circle. Oh, that's not too bad. So that's supposed to be a circle. All right, so let's move on to the next example. All right, example 5, convert the polar form to rectangular form, and again, we're gonna have to sketch its graph. So we're just given r equals -2, and then we need to sketch this. For this particular case, I think we can sketch this without converting into a rectangular form, but we're gonna have to do that anyways. But think about it. Do you see a r? I mean, just kidding. Yeah, we see a r. Do you see any theta? No. So that means that no matter what the value of theta is, our r, our radius is always going to stay as -2, which means that we're just going to have a circle of radius 2. So let's prove that by converting this polar form into a rectangular form. Alright, so somehow I need to replace that r in terms of x and y. So when it comes to r, only equation that I know is r squared equals to x squared plus the y squared. So I'm going to force that to appear by squaring both sides. So let me just write that out. Square both sides to get r squared. All right, so let me just copy and paste our original equation. Now, I'm going to square this. If I'm going to square the left-hand side, I better square the right-hand side. So, what is it going to be? We got r squared equals to 4. But the thing is, r squared is nothing but, let me just write it over here, r squared is x squared plus the y squared. Now, this is all going to be 4. So that is the rectangular form. Now, oh my gosh. Now, can you tell what kind of figure that is? As we expected, yes, this is a circle centered at 0, 0, 0, and the radius of 2. Just as we expected. So here is that perfect graph. Okay, so I'm just going to check in with you and see how you're all doing up to here. Because we need to go over one more very, very important theorem, which is the slope in polar form. So if you feel like you're burnt out a little bit, I'm pretty sure that you are, because I'm pretty burnt out right now myself. Stop the video and just rest a little bit, and then come back and we'll learn about the slope in polar form. Alright, so let's get down to business. So our next topic is slope in polar form. The theorem says that if f is a differentiable function of theta, then the slope of the tangent line to the graph of r equals f of theta at point r comma theta is given by dy over dx equals dy over d theta all over dx over d theta, which equals to WTF, where dx over d theta does not equal to 0. I know that the last expression looks kind of scary, but do not worry about it because I will try to explain everything why that formula holds. So for the setup of this, we're assuming that r is a function of theta, so r equals f of theta. Now, let's go back to the conversion formula for x and y. So we had x equals r cosine of theta, and then our y equals to r sine of theta. All right, but the thing is, in this portion, we're assuming that r equals to f of theta. So I'm going to replace our r with f of theta now. Okay, so in that case, what we're going to get is r is f of theta times the cosine of theta, and y is going to become f of theta multiplying here by the sine of theta. All I did was replace our r with f of theta because that is the setup. Now let me write this a little bit nicer. So what do we got? Our x becomes f of theta times the cosine of theta. Now let's differentiate this. So dx over d theta, remember, this we're going to have to apply the product rule to f of theta multiplying by cosine of theta, right? Because here's one function, here's another function. All right, so if I take the derivative, I'm going to apply the product rule. So we're going to have f of theta multiplying here by the derivative of cosine, which is negative sine of theta, and then plus cosine of theta multiplying here by f prime of theta. So that is our dx over d theta now. All right, and furthermore, we have our y is f of theta and then sine of theta. So that implies that dy over d theta, again, we're going to apply the product rule. Here's f of theta times sine of theta. So here we're going to get f of theta times the derivative of sine, which is cosine, and then plus the sine of theta multiplying here by f prime of theta. All right, so let me just box these two. Okay, so putting this all together, remember our dy over dx is dy over d theta all over dx over d theta. So if I replace our dy over d theta, since I'm running out of room, I'm just going to make an arrow here. So if I replace our dy over d theta with this expression on the top, and then also if I replace the dx over d theta with the expression that we got over here, so I'm going to take this, where is it? Right here. Then do you see that we're going to get exactly the same formula as stated above? I know, I'm sorry, this looks really nasty, so I will re-explain it on the next page. All right, so again, our setup is r equals the function of theta, and we know that our x is r cosine, and then our y is r sine of theta. But the thing is, r is f of theta, so I'm going to replace our r with f of theta now. So we get f of theta cosine of theta. On the bottom, we're going to have r is f of theta, and then we're going to have sine of theta. All right, so now if I differentiate this, then what we're going to get is dx over d theta. We're going to apply the product rule to get f of theta multiplying here by the derivative of cosine, which is negative sine. So you know what? Let me just bring the negative sign on the front. So you got negative f of theta, sine of theta, and then plus cosine of theta, multiplying here by the f prime of theta. And then doing the same thing for our function y. If I differentiate this, our notation is going to be dy over d theta, which is same thing as f of theta, multiplying here by the derivative of sine of theta, which is cosine, and then plus sine of theta, multiplying here by the derivative of f of theta, which is f prime of theta. Okay, so now since our formula for the derivative is just like the parametric form, so remember dy over dx, this is same thing as dy over d theta, all over dx over d theta. In parametric form, I did use theta as a parameter, but usually it was denoted by t. T was the parameter, so we had a dt on the bottom. But anyways, so let's just plug them in. So if I plug our dy over d theta, then we're going to get f of theta cosine of theta, and then plus sine of theta multiplying here by the f prime of theta, and whole thing dividing by dx over d theta, so that will be negative f of theta and sine of theta, and then plus cosine of theta multiplying here by the f prime of theta. And this is how that nasty looking formula was formed. So let me just box that. Alright, so are we ready to do some examples? Let's do this. Example 6, find the points of horizontal tangency in polar coordinates and also in rectangular coordinates to the curve r equals 3 sine of theta. So here, what the question's asking you is to, of course, compute the derivative, set that equal to 0 to find the horizontal tangency. But in polar coordinates and rectangular coordinates, so we're looking for points in polar coordinates, which is given by r comma theta, and we're going to convert that into a rectangular coordinate, which is x comma y. So we want both representation for this. Alright, so let's do this. So first step is this. Bust out your conversion formula for x and y in terms of cosine and sine. So first step, x equals r cosine, and then our y is r sine of theta. Now notice that our r is 3 sine of theta, isn't it? So what we're going to do is we're going to replace that r with 3 sine of theta. So this is exactly the same thing as 3 sine of theta. That's our r. And then multiplying here by the cosine of theta. And we're going to do the same thing for the y. So y is r sine of theta, but r is 3 sine of theta. That's our r. And we're going to have to multiply here by the sine of theta. So let me see. Now since we need to differentiate, so let me just simplify this into 3 sine square of theta. Alright, so now I think we're ready to differentiate. So let's go with dx over d theta. Alright, so when I do this, let me factor the 3 out. And I'm just gonna take the derivative of sine times the cosine. So ready? Another product rule. So we're gonna have sine of theta times the derivative of cosine is negative sine. Negative sine of theta. And then plus the cosine of theta times the derivative of sine is cosine of theta. So what do we got? So this is same thing as 3. And then we're going to have negative sine square of theta and then plus the cosine square of theta. Alright, so that is our dx over d theta. So let me just box this because I need this piece of information. Alright, now we're going to do the same thing for our function y equals r sine of theta. So now we're going to go dy over d theta So now we're going to have to differentiate 3 sine square of theta. So again, I'm going to factor the 3 out. And then let's just differentiate sine square of theta. So if I differentiate that, we're going to have to apply the power rule first, so which is 2 times sine of theta to the first power, multiplying here by the derivative of sine, which is cosine of theta. So what do we get? So we're going to have 6 sine of theta and then cosine of theta. So that is our dy over d theta. So I'm going to box that as well. Alright, so therefore, let's follow the formula for the dy over dx. So our dy over dx is dy over d theta all over dx over the d theta. So the dy over d theta is 6 sine of theta, cosine theta, whole thing divided by, dx over d theta is 3 times, let me just write it as cosine square of theta minus the sine square of theta. Alright, now let's just simplify a little bit. So we got 2 sine theta cosine of theta, whole thing over cosine square of theta minus the sine square of theta. Boom, so that is our dy over dx. I'm gonna box this. Alright, so now the question's asking us to find the horizontal tangency. So horizontal tangency means that horizontal tan implies that we're gonna have to set dy over dx to go to 0. So that means that our numerator has to go to 0. But let me write every step out. So that implies that we're gonna have 2 sine of theta cosine of theta all over cosine squared minus sine squared has to go to 0, which implies that our sine of theta cosine of theta has to go to 0. Yes, I know there was a 2 in the front of it, but I already divided by 2 on both sides. Alright, so that implies that either sine of theta is 0 or the cosine of theta is 0. Oops, you know what? I forgot to write as a part of the problem that theta is between 0 to 2 pi. Sorry about that. Alright, so sine of theta is 0. That's when theta is 0 and a pi. And then cosine of theta is 0 at when theta equals to pi over 2 and 3 pi over 2. So let me just box that. So far so good. Now I'm going to run out of the page, so I'm going to go on the next page to continue this problem. So we concluded that dy over dx equals to 0. That implies that our theta is going to be either 0, pi, or pi over 2, and 3 pi over 2. Alright, so let me box this. Great, so we got our thetas. Now we need to compute our corresponding value for r at each theta. So to do that, we need to go back to our original problem. So what the heck was our original problem? And so that was, our problem was, equation was what? R equals to, what was it? 3 sine of theta? So that was our equation, wasn't it? Alright, so keep that in mind. Alright, so now let's compute when theta is 0, what is our corresponding value for r? So our r is going to be 3 sine of 0, which is 3 times 0, so this is going to be 0. So therefore, our r comma theta is going to be, r is 0, theta is also 0. Okay, so now next, when theta is pi, our r is 3 sine of pi. Sine of pi is 0, so here you're going to have a 0 again. So therefore, what do we get? R comma theta is, r is 0, and theta is pi. All right, next, theta equals to pi over 2. R is 3 sine of pi over 2, so that will be sine of pi over 2 is 1, so we're going to have 3. So therefore, our r comma theta, be careful with the ordering. Okay, so r always comes first, so here you're going to have 3 comma pi over 2. And when theta is 3 pi over 2, our r is 3 sine of 3 pi over 2. Now what is the sine of 3 pi over 2? That's negative 1. So here what we're going to get is negative 3. So therefore our r comma theta, this is going to be r is negative 3 and our theta is 3 pi over 2. Now let's take a look at 0, 0 and 0 pi. I believe that they're going to represent the same exact point because, let me see. So this is when radius is 0, theta is 0, so it will be here. And the radius is 0, our theta is pi, but the radius is 0, so it's just going to be dot at the origin. So they represent the same point. So what I'm going to do is I'm just going to take one representative. So I'm going to say these are the same. I'm going to take one representative. So I usually take the nicer looking one, which is 0, 0. Now, let's take a look at the last two r comma thetas. So if I plot that, the radial line is going to be at 3. All right, so the 3 comma pi over 2, I'm going to start from positive 3 and then go pi over 2 units. So we're right here at this dot. Now, negative 3 comma 3 pi over 2. So I'm going to, if I start from negative 3, go 3 pi over 2, do you see that I'm going to end up at the same point? So here, these 2 points are exactly the same. So again, we just need to take one of the representatives. So I'm going to take the nicer looking one. To me, 3 comma pi over 2 is nicer looking than negative 3 comma 3 pi over 2. But either one's okay. So what we just concluded is that, therefore, our function r equals 3 sine of theta has a horizontal tangency at, now these are in terms of a polar coordinates now, so r comma theta is 0, 0, and, sorry, that was an and, r comma theta is 3, 2, 3 comma pi over 2, sorry about that. All right, so I'm going to box that. So this was in polar coordinates. All right, now the question asks you to convert this in rectangular coordinates as well. So now let's take a look at how to do that. So now let me just write down. All right, so we want to somehow convert this in terms of x and a y. That's going to represent the same point. Well, if r comma theta is 0, 0, then x comma y should be 0, 0, but let's just do this formally. So again, we're going to have to bust out our conversion formula, which is x equals r cosine of theta, and then y is r sine of theta. And we're going to plug in when, let me see, let's just take care of when r comma theta is 0, 0. So this will be our case 1. So here what we're going to get is r is 0 times cosine of 0, so which is going to be 0. And over here we're going to have r is 0, and then sine of 0 is 0, so how boring. 0, 0, as we expected. All right, so together what we're going to get is when r comma theta is 0, 0, our x comma y is also going to be 0, 0. All right, so now let's go with when r comma theta is 3 comma pi over 2. All right, so we're going to do the same thing. So x equals r cosine of theta, y equals r sine of theta. All right, so then our r is 3, and then here you're going to have cosine of pi over 2. And cosine of pi over 2 is 0, so looks like we're going to have a 0. And for y, we're going to have r sine of theta, what r is 3, and then sine of pi over 2. Sine of pi over 2 is 1, so we're going to get 3 back. So, therefore, what we're going to get is x comma y is going to be 0 comma 3. So let me just box this. Let me just All right, so looks like we're only gonna get 2 points of horizontal tangency. So let's just take a look at our equation r equals 3 sine of theta. Maybe we can convert that into a rectangular form, and we can prove that there are only 2 horizontal tangency. So just for fun, let's convert this into a rectangular form. All right, so rectangular equation, I should say. What was our function? R equals 3 sine of theta. All right, I think we've done some similar example of this earlier. So do you guys remember what the trick was? Remember we put a star right next to it because that's a common final exam question for second semester calc? Yes, we need to multiply both sides by r. That was the trick, so make sure to know that trick. So let me just copy down our function. R equals 3 sine of theta. Now I'm going to multiply both sides by r again. So I'm going to insert our r, and then I'm going to multiply here by r. Then what we're going to get is r squared equals 3r sine of theta. But remember, r sine of theta, what is that? That is nothing but our y. So this becomes y now. And furthermore, our r squared is x squared plus d y squared. So using all of that, we're going to get x squared plus y squared equals to 3y. So let's complete the square on the y now and see what we're going to get. So let me just bring this guy over here. All right, so we got x squared plus y squared minus 3y equals to 0. Now it's gonna go x squared plus y squared minus 3y. I'm just gonna leave a little room and then put equal to 0. Now what I'm going to do is I need to complete the square, so I'm going to divide this number by 2. You're gonna have negative 3 over 2. What you need to add in here is negative 3 over 2 squared, so which will be positive 9 over 4. That means I'm going to add 9 over 4 on the right hand side of the equation as well. So this is going to become x squared plus y minus 3 over 2 squared equals 9 over 4. All right, so again, can you tell me what kind of equation this is? This is the whole reason why we studied conics in previous section. But anyways, isn't this an equation of a circle again? So this is going to be a circle centered at, where is that? 0, 3 over 2, and the radius is 3 over 2. So let's just try to draw it out. So the center is at 0, 3 over 2, so 0, 1.5, so maybe here, around here. So this is our center, 0, 3 over 2, and the radius is also 3 over 2. So that means that we're gonna have to go down here and then over here. Does it look right to you? And then from the center, I'm gonna go 1.5 units out and then 1.5 units out this way. Oh goodness. All right, so now if I, oh my God, Okay, this is supposed to be a circle. Pretend that this is a circle. All right. Now, let's take a look and see if this makes sense. Our answers make sense. So we see that we do have a horizontal tangency here at this point, and then also at the very bottom point. All right, so does that make sense? Well, yes, because this point here is nothing but a 0, 0, right? And then 0, 3 is right here. So it does make sense. All right, so I am pretty sure that you're completely burnt out. Anyways, I'm going to stop here, so make sure to go over all the examples that we just went over for this section, and of course on the previous section as well. And if you have any questions at all, please let me know. And those of you who sat down and watched this whole entire video, you guys are freaking amazing, because I am here completely brain dead right now. So I can't even imagine how you guys are feeling. But anyways, good job, and tell yourself that you are awesome, because in my book, you all are freaking awesome. And that's all I gotta say.